Can I test my sound? Is my sound okay?
Sound is perfect. Yes, Venus, are
Great.
you happy?
Thank you.
Okay, so I just want to welcome our YouTube viewers. We are very blessed to have each and every one of you with us. And before we introduce our speaker, we just wanted to share with you how important it is to know that you are part of this program this evening. So please know that even though this is your first time maybe joining us or maybe your 100th time, you are one of a kind and we appreciate it. So please listen to the program we have tonight or daytime, wherever you find yourself. So we're going to introduce our speaker. Dr. Ryan Hayes has been on before, and we are so happy that you joined again. We were looking forward to for part two. People were asking, when are you coming back? So just want to share for those who haven't heard about you yet, especially our viewers. You are practicing chemistry for over 30 years now, and you are currently a teacher at Andrew University, has three kids and a beautiful wife named Susie, who is also joining you in sharing the gospel and the three angel message. Your bio is long, and we know you kind of come back for the rest, as we know now there's 7 parts, not just 5. And we are very happy about that. So we are looking forward to what the Lord is going to share with us. So if you would mind to share with us the message, and then after that, do the closing prayer. And then unfortunately, we have to greet and say goodbye to our YouTubers. Then we're going over to our platform. So YouTubers, please listen with us as the panel will be joining as well. And then we're giving over to you now, Ryan. Thank you very much once again.
Oh, it's great to be here. And hello from Michigan. We're finishing up our church service. I'm in the mother's room. The light was a little dimmer than I thought, but hopefully you can see me. But most of all, I just need to be able to hear, and I'll share some slides. So if I could do that right now, I would like to try to do that. Let's see if I can get that one going and share the screen. We're enjoying our Sabbath day here. The weather is fantastic. And let's see if this will work here. All right, let me know. Can you see the screen okay? Is that working? Great. Excellent. At some point, I may show a little video or two and to help illustrate some points. So I want to make sure I share my sound at the appropriate time here. And there we go. Okay, so thank you for having me back. So I am a chemist, and I'm going to be talking about trees, though. So as you might imagine, I'm going to talk to you about some of the chemistry of trees. And there's some amazing things that are going on that reveal God's hand, that God is our creator. And I wanted to share about that. So this one's entitled Moving Water Uphill. And there's some surprising things that I want to share to you about trees and the chemistry that takes place in there that I think will help reaffirm your belief in a creator. And so one of the things that I've been looking at for the last 10 years or so is how do we see God's hand? And broadly, this is looked at in this topic called intelligent design. And it's really interesting. And I'll share this every time just to make sure we get this point. It's okay to look for the designer of a hand, someone's mind, their hand at work, if you're doing archaeology. Hey, was this rock designed, or did it happen by chance? We can go to crime scenes, and it's science to go, hey, did this happen by someone's mind, devious mind, or did it something happen by chance? People are looking for signs of intelligence out in outer space. You can do those things, and it's science. You can look in so many different areas of our world, and it's science to be able to decide if there was a mind there or did it happen by chance, by nature. And so those are very important aspects. But if you try to look for design in biology or chemistry, you are not a scientist. They will kick you out of the academia, they won't publish papers, and there's a real resistance to look at design. And I think part of it is we just don't fully understand biology and chemistry to the complete depths. And they feel like people are giving up and saying, oh, there's a God. You're not really looking at it. And I'm trying to say, no, when we look at the design, and actually not because we don't know how things work, but because we know how it works, that they need a designer. So it's not an argument of God of the gaps. It's an argument from knowledge of how things work. And that's what we're going to try to do here today. And just for a few minutes, to speak to the earth, as Job 12 has encouraged us to do, to talk to the animals, talk to the planet here. And that's science. Learn how they work, how do they communicate. And when you do, you'll realize and you'll be able to say, who among all these does not know that the hand of the Lord has done this? And in whose hand is the life of every living thing and the breath of all mankind? And so that's my inspiration verse that inspires me to keep looking for God in the world around us. Now, a little over 20 years ago, Michael Behe, this biochemist, introduced this idea, and it's been a very powerful one called irreducible complexity. And he basically summarized it as you can tell if something's designed if there's all these parts and they all have to come together at the same time. And if we see evidence of that, then that's probably evidence of a designer. Because if you take away one part from a mousetrap, it won't work as a mousetrap anymore. It'll cease to function as that. And so there's all these parts that need to happen at the same time. So this is partly what's behind what I call chemical design, when we see all the parts that are working together. And we're going to put that together now with some concept of how a tree moves water uphill. And it's maybe more amazing than we ever thought it could be. And so some people don't see that this is an argument for design, but I think it's actually a very powerful one, and one that many people are starting to also agree if you see irreducible complexity. I won't go into the challenges to that irreducible complexity because I think there's some amazing things we just need to focus on. Now, moving water uphill is a very big challenge. You have to overcome lots of forces, how heavy it is, gravity. It's very hard to move water uphill. But that's so important for our planet to be able to move water uphill because it will provide water to many places along the way as water comes down as rivers. Now, much of our water that gets uphill or goes up into the skies from evaporation of water, and it turns into clouds and rains. And so it's, it's quite a feat though, and you need a lot of energy to do that. And so there's ways to accidentally move water uphill, of course, splashing around and, tides and things that can move, various amounts of water, but it's not very consistent, not very reliable. Now, one of a force that can help move water uphill is called capillary action. And I think I'm going to skip this video. Well, here's a video of water actually moving uphill. There was a place where these guys were putting the water down on...
Situated at the heart of Machakos in eastern Kenya, stands a phenomenon so strange that not even experts have been able to demystify. The Kituluni Hills, approximately an hour's drive from the country's capital, Nairobi, popularly known as the Anti-Gravity Hills, has defied the laws of nature, as we know. For a car, it requires much effort to go downhill than uphill. Water here will flow uphill to the amusement of many.
Okay, leo nimeona maajabu na nilikuwa nasikia area hii ya Ukambani kuna mahali ambapo maji ikimwagwa badala iteremke inapanda, na nimehakikisha ni ukweli kwamba nimeona maajabu.
And so this place, it looks like water is flowing uphill. And this gentleman here said it was a miracle that it was flowing uphill. And it really is a miracle if water could go uphill. And it might be due to capillary action. What is capillary action? It's this property of water. Water is kind of sticky to itself, and it wants to cling to itself, and also wants to cling to materials like it, like cellulose or glass, and it'll start climbing. And we've all kind of experienced that. You can put paper towels into some water, and it'll start to go uphill. But there's a limit to what capillary action can go. And it's about 10 meters high or 34 feet tall, depending on what units you like. And that's because air pressure will eventually start to become too heavy, and there's just not enough pulling force. But capillary action is this tiny little tubes where water can go up. And so trees and plants will take advantage of this. But that's only one part of this pulling force that helps to pull water uphill. So that's part of it, but only a small part. There's a second part that I find super exciting, and it's called osmosis. And this is a property that of water and liquids where it will push liquids uphill. You really need special liquids like water to do this. The way that it works is it's a pressure that is occurring in the roots of plants and, of course, trees. And it's a desire of water to actually go from a pure side to an impure side. And when it does that, it will push water uphill. And scientists know even how to calculate the force. I teach it in my class. It's called osmotic pressure. And I'm not going to go through all the calculations for you. This is one of my slides from my class. And we said pressure water can go through a special membrane. And this is one of the key things. It needs a special semi-permeable membrane in which only water can go through and nothing else can go in or out. And when that happens, water will go inside of this. It can go inside of a tube and it will push up and it will overcome air pressure. So this is way more powerful than capillary action. And so I did some calculations for my students in class. I'm just going to run through. I'm not going to even tell you what it is. I'm going to tell you the conclusion of the calculations. It's something anybody can do. And if you use a concentrated sugar, because that's what plants do, they make sugar and they can make concentrated sugar. And when you use that calculation, osmotic force is so powerful, it can push water up almost 2 kilometers into the air, over a mile. It's amazing. It is super powerful, and it's pushing up from the roots. But in order for that to happen, and I just, as an example, some of our tallest trees are 100 meters, just over 100 meters. So that means, if you can push up to 1,000 meters, you got plenty of pushing power for osmotic pressure. And I like to do this for my students. I'll take a semi-permeable natural membrane, a root vegetable like potatoes, and I'll drill out the middle, and I will put some sugar in there or corn syrup, and I'll just set it into some pure water. And that pure water wants to go in and dissolve the sugar. And when it does, it starts to move up the tube. So I've simulated it here. And this is a picture of one of my potato experiments. You can use all sorts of vegetables for this. It's really cool. But the thing is, it's really slow. And so it took a couple of, I can move about an inch, a couple of centimeters in an hour. And it takes a long time, but it can push and it will push uphill. It's pretty amazing. And so that's a lot of fun. But in order for this to happen, you got to have a very special membrane that's so small in its pores that only water can get through. Water, thankfully, is one of the smallest molecules known to man. And so it can go through the membrane and nothing else. And when that does, that's what pushes water up. And so we're so thankful for the amazing properties of water. And one of its key things is that it's small. If we were made out of a liquid that was much larger than water, a lot of these things wouldn't work. And so water is so important because it's so small. Now, nature regularly makes these amazing semi-permeable membranes. We call them roots vegetables. And so you can do this experiment with anything that's a root. But that design, we just take it for granted that it just does this. But it's such an amazing property for only water to get through and nothing else. Now, because of that, we get this amazing pushing pressure. But that's only part of it. There is a third part that takes place that at the leaf level, there's this process called transpiration. It's this evaporation of water occurring from the leaves. And that helps to pull the liquids up. But even that is only part of it. There's a really amazing video that hopefully we won't get in too much trouble for showing. I don't think so. It's from Veritasium, and I'm going to show maybe bits and parts. I'll just show it here. And I may have to talk a little bit about it, but it's how trees use another process from physics to overcome all of these forces of gravity and things to move water uphill. And so let's see if we can watch a little bit of this.
Sometimes the simplest questions have the most amazing answers. Like, how can trees be so tall? It's a question that doesn't even seem like it needs an answer. Trees just are tall. Some of them are over 100 meters. Why should there be a height limit? I'll tell you why. Trees need to transport water from their roots up until their topmost branches in order to survive. And that is no trivial task. There is a limit to the height that water can be sucked up a tube. It's 10 meters. If you suck on a long vertical straw, the water will go no higher than 10 meters. At this point, there will be a perfect vacuum at the top of the straw, and the water will start to boil spontaneously. For a tree to raise water 100 meters, it would have to create a pressure difference of 10 atmospheres. How would trees do that? When I posed this conundrum, a lot of people said the answer is transpiration. And that's when water evaporates from the leaf, pulling up the water molecules behind it. Now that's clearly a mechanism a tree can use to create suction, but it doesn't help us overcome this 10-meter limit.
The lowest the pressure can go is a pure vacuum, which I imagine is not happening inside of tree leaves. Right?
Right, Hank. So you might suspect that a tree does not contain continuous straw-like tubes.
The tree effectively has valves in it, so you don't have a column of water.
This big tube, which you're saying needs to be filled with water, is actually made up of cells.
Although these are good speculations, they don't turn out to be correct. Scientists who study trees find that the xylem tubes that transport water do contain a continuous water column. So how else could the tree transport water from the roots to the leaves?
They don't suck. They don't use a vacuum.
Okay, so how do they do it?
Squeezing like a cow, like you're squeezing a cow udder all the way up. There's little tree muscles in there.
Yeah. Besides being a giant waste of energy, all of the cells that make up the xylem tubes are dead. What about osmotic pressure? If there is more solute in the roots than in the surrounding soil, water would be pushed up the tree. But some trees live in mangroves where the water is so salty that osmotic pressure actually acts in the other direction, so the tree needs additional pressure to suck water into the tree. Then it must be capillary action. The thinner the tube, the higher the water can climb. But the tubes in a tree are too wide. At 20 to 200 micrometers in diameter, water should rise less than a meter. So how do trees do it? Well, one of the assumptions we made is wrong.
The lowest the pressure can go is a pure vacuum. Pure vacuum. Pure vacuum.
In a gas, this is true. When you eliminate all of the gas molecules, the pressure is zero, and you have a perfect vacuum. But in a liquid, you can go lower than zero pressure and actually get negative pressures. In a solid, we would think of this as tension. This means that the molecules are pulling on each other and their surroundings. As the water evaporates from the pores of the cell wall, they create immense negative pressures of minus 15 atmospheres in an average tree. Think about the air-water interface at the pore. There is 1 atmosphere of pressure pushing in and negative 15 atmospheres of suction on the other side. So why doesn't the meniscus break? Because the pores are tiny, only 2 to 5 nanometers in diameter. At this scale, water's high surface tension ensures the air-water boundary can withstand huge pressures without caving. As you move down the tree, the pressure increases up to atmospheric at the roots.
All right, I'm going to pause it right there, just so hopefully we don't get in trouble from showing Veritas, and you guys should go and watch that. But there's this concept called the negative pressure, and Derek here is trying to outline it. And trees have this incredible design to hold water in and create these negative pressures that help pull the water all the way up. So it's all of these forces all together, but probably mainly this negative pressure. Now, in order to do all of this, you have to be able to, I had a plumbing picture coming up here. Well, I'll get to that in a second. It reminds me of plumbing. In order to move water, you've got to have everything so airtight and watertight so that it won't leak and you don't get air in there. And that is such an amazing design to be able to do that. So now we started thinking about, why would you move all this water? Is it just for the tree to move this water up? And there's something interesting that shows up about trees that people didn't really think much about, is that most of that water that comes up, and it's actually at the end of that video, 90% of the water that comes up into a tree just evaporates and goes out into the air. And that almost doesn't make sense. You think if someone was designing a tree just to bring water up for itself, because it needs that for photosynthesis, that would be kind of a waste, that you would be losing 90% of the water to the atmosphere. And this is actually one of the interesting things about the design that I didn't think about until I started thinking about trees. And I think in this next video here, why would you move all of this water? So there was something that I was missing about trees that I didn't understand. And I think this little video right here will help tie these concepts together.
All around the world, traditional wisdom has it that forests bring the rain. Scientists have scoffed at this notion for a while. Forests grow where there's ample precipitation, but they do not cause that precipitation. It comes because of winds that are governed by geomechanical processes which have nothing to do with where the forests are and aren't. Water does not tend to stay in one spot for very long. Most of it ends up running off into the ocean via rivers. Unless there's some way for the moisture from the ocean to come back inland, all of the land's water would be gone very quickly, as would the forest. According to the geomechanical view, moisture gets transferred inland when water vapor is carried from the ocean by winds. Because some of this water gets lost to precipitation, the deeper inland this air gets, the less moist it becomes. Therefore, deeper inland means less rainfall. If this view is true, we should expect to only see forests near the coasts, and drier, more arid areas the farther inland we go. But this is not what we find. Where there are still natural forests, precipitation does not decrease with distance from the ocean. In fact, it often increases, the greatest amount of rainfall being in the deepest parts of the forest, sometimes thousands of miles from the coast. This is unexpected and difficult to explain with the geomechanical view. What on earth could be attracting so much water to a spot so far from the ocean, and why? While there is more water in the ocean than in forests, forested areas have more water vapor in the air. This is because forests, especially healthy ones, have a lot more surface area for water to evaporate off of. Multiple canopy layers, shrubs, moisture-laden ground are all full of water, which transpires or evaporates, entering the air. As a result, we find much more water vapor in the forest, even when there's less total water. The ample amount of water vapor in the forest rises and condenses into clouds, changing from gas to liquid. This creates a drop in air pressure, which allows even more vapor-filled air to rise. This creates an upward air current, which in turn creates a horizontal current closer to the ground. This sucks in air from higher pressure areas, like the air from over the ocean. This air contains some water vapor, which increases the total amount of water in the forest, leading to more frequent rainfall. Essentially, forests create a giant constant air current that attracts moisture from hundreds of miles away. This is how we find so much water so far from the ocean. The forests bring it in. This process is known as the biotic pump, and it shows how traditional wisdom was right all along. Forests really do bring the rain. So as more forests are clear-cut, the more extreme become the droughts, and the more expansive become the deserts. If we want to thrive on this planet, we need to preserve and regenerate the forests. All around.
And so to me, that blew my mind, is to think about all of the trees as being these pumps that are pumping air into the atmosphere. And of course, the plumbing has to be great. I hate plumbing. I don't know if there's any plumbers in this group here, but plumbing, in theory, I understand, you just hook these parts together, but everything I have tried to plumb always leaks. Always leaks. I'm using Teflon tape and putties, fitting it, trying to get through, and it never works. It always leaks. I get so mad. You can ask my wife. She says, "Don't do any more plumbing." I don't know why. It always leaks. But if there was any leak in a tree or in a plant, none of this water movement would ever work. And what we need to start seeing trees, they're these amazing things, but they're also a pump. And if we were to look at a pump, even the simplest pump, we're like, yeah, somebody designed that. You've got a crank there, you got to get the plumbing right, you got to get all the parts, and then, yeah, you can start moving water uphill. But when we look at a tree, we're like, yeah, that just sort of happened by chance, evolution over millions of years. And yeah, no, a tree is the sophisticated pump that is pumping up water up to its highest parts, not just for itself, but for the planet. It is a sprinkler that is spraying water up into the air to help make sure not only where it is planted, but in other locations around it, that the forest is a big sprayer of water up into the atmosphere. And so someone who's designing a planet would create water pumps to help push water uphill and up into the atmosphere. And this global view of what a tree is truly amazing. And that starts to make sense. Why would trees be designed to release most of its water up into the air? Because it is a sprinkler. It is a water sprayer of to get the humidity in various parts where they're too far away from large water features like oceans or large lakes. And so that to me started to change the perspective of how I start looking at nature. And I see design here because all of these parts need to happen. Semi-permeable membrane, you got to get water to come in, but just water. You don't want a bunch of other dirt and crud and stuff to get in there. And you've got to be able to have the right size tubes and pores and things in there. And on the leaves, if everything was too big or too small, the water wouldn't move up. And you got to have it airtight and watertight, or you wouldn't get water to move. And this stuff has to be strong enough to withstand air pressure and the movement of wind and things. And so all of this coming together speaks so loudly to a designer, because to have just parts of it at time, the tree wouldn't survive. So we need all of these parts to happen at the same time. And to end our time, I'm reminded of Psalms 104. It says, he waters the hills from his upper chambers. The earth is satisfied with the fruit of your works. He causes the grass to grow for the cattle and the vegetation for the service of man, that he may bring forth food from the earth. These plants are wonderfully designed. Trees are wonderfully designed to be these big water pumps to water the earth. And it's so amazing to me because we just see it's trees. Yeah, they're really cool and we can build stuff from them, but they have a very important role in watering the earth. So I wanted to just share that with you guys, just another perspective of trees and how they're amazing. And there's much, much more to share. But I don't know, should we end with prayer now or take a few questions? Let's end with prayer. All right, so let's end with prayer. Father God, I just want to thank you for making such an amazing plants around us. And we see your design. These things can't happen by chance because they would fall apart or something wouldn't work. And so we thank you for that, for watering the earth and for providing food and water for us using these living organisms there. So we're just so grateful for them. Thank you for blessing us in our time together. Thank you in Jesus' name. Amen.
What a wonderful message. It's so wonderful. I'll definitely keep on looking for trees in different ways. I love trees, and I just wanted to say goodbye to our YouTubers, and we would like to invite you to join us on the platform one time when you are able. But until then, please use the YouTube link to keep on listening on YouTube. We want to say thank you and hope that you'll join us from other programs and just go to the website and see you can stay up to date what's going to happen. Bye-bye, YouTubers.